Today we are solving a hard LeetCode problem, counting pairs of subsequences that never share an element but end up with the exact same greatest common divisor. Sounds scary, but we will crack it with one tool, dynamic programming, where we track just two small numbers as we walk through the array. Let's meet the tools first. First tool, the greatest common divisor, or GCD. Think of cutting two ribbons, one 12 inches and one 18 inches, into equal pieces with nothing left over. The biggest piece that works is 6 inches, so the GCD of 12 and 18 is 6. One handy convention, the GCD of 0 and any number is just that number, and we will lean on that trick later. Second tool, a subsequence. Imagine highlighting some words in a sentence. You can skip words, but you never reorder them. From the array 1, 2, 3, you could pick just 1 and 3. That is a subsequence. Disjoint subsequences simply means two highlighters that never touch the same word. Third tool, dynamic programming, or DP. It is like filling in a spreadsheet. Each new cell is computed from cells you already filled, so you never redo work. Instead of trying every possible pair of subsequences, which would explode, we will keep a table of counts and update it one number at a time. In short, DP means remember what you have counted so far, and build on it. Here is the task. From the array, pick two groups of elements. Rule 1, no position of the array can be in both groups. Rule 2, the GCD of group 1 must equal the GCD of group 2. We count every valid pair, and because the count gets astronomically big, we report it modulo 10 to the 9th plus 7, which is just a standard way to keep numbers small. Let's walk the example 10, 20, 30. Give the 10 to group 1, so its GCD is 10. Give 20 and 30 to group 2, their GCD is also 10. Match. Now swap which group is called first and which is called second, and that counts as a different pair. Those are the only two matches, so the answer is 2. Here is the trick. Walk through the array one element at a time. Each element does exactly one of three things: join group 1, join group 2, or stay on the bench. Every possible pair of disjoint subsequences is just one particular sequence of these choices. So instead of picking subsequences, we count choice sequences. In short, 3 doors per element, and we count paths through the doors. You might wonder, don't we need to remember which exact elements went where? No. To check the final rule, all we need is the current GCD of group 1 and the current GCD of group 2. Since values are at most 200, each GCD is a number from 0 to 200. So our whole memory is a small grid. DP at row A, column B, stores how many ways we reach GCD A in group 1 and GCD B in group 2. 0 means the group is still empty, and remember, GCD of 0 with X is just X, so an empty group absorbing its first element works automatically. We build a 201 by 201 grid of zeros. Why 201? Because values go up to 200, and we need slot 0 to mean the group is empty. We set DP at 0, 0 to 1, because before touching any element there is exactly one situation, both groups empty. That single one is the seed every other count grows from. For each element X, we make a copy of the table. The copy already handles door 3, skipping, because skipping changes nothing. Then for every state A, B that has some ways, door 1 sends X into group 1, moving us to row GCD of A and X, and door 2 sends X into group 2, moving the column the same way. Notice why we write to a copy instead of the live table, otherwise the same element could sneak into a group twice. We also skip zero count cells purely for speed. After all elements are placed, DP at G counts the pairs where both groups ended with GCD exactly G, equal GCDs live on the diagonal of our grid. We start the loop at 1, not 0, because dp at 0, 0 would mean both groups are empty, and the problem demands non-empty groups. A group with any element in it can never have GCD 0, so starting at 1 quietly enforces non-emptiness for both. Sum the diagonal, apply the modulo, done. Quick confidence check with all ones. Every non-empty group has GCD 1, so any split works. For elements with 3 doors each gives 81 total assignments. Remove the ones where group 1 is empty, 16, and where group 2 is empty, another 16, then add back the one case we subtracted twice, where both are empty. 81 minus 32 plus 1 is 50, exactly the expected answer. Our DP computes this same number without us doing the algebra. The obvious alternative, literally enumerate every way to assign elements to group 1, group 2, or bench, compute the 2 GCDs, and count matches. The plus side is that it is trivially correct and takes 5 lines. The minus side is brutal, 3 to the power of n assignments. At n equals 15 that is already 14 million, and at n equals 200 the universe ends first. Great for testing the real solution on tiny inputs, useless for the actual constraints. The DP visits each of the 200 elements and, for each, scans a grid of about 40,000 cells, so big O of n times 200 squared, roughly 8 million cheap operations. Space is just the grid, big O of 200 squared. The brute force is big O of 3 to the n. So you would pick brute force only to cross-check tiny cases while developing, and the DP for everything real. 3 traps to check. 1 element, you cannot form 2 disjoint non-empty groups, and indeed DP at G stays 0, so we correctly return 0. Duplicate values like all ones, no problem, because our DP walks by index, and disjoint means different indices, not different values. An overflow, counts explode fast, which is why we apply the modulo on every single addition rather than once at the end. In short, the structure of the DP handles the traps for free. Let's land the plane. Every element picks one of 3 doors, group 1, group 2, or the bench. The only memory we need is the pair of running GCDs, a tiny grid of counts, and dynamic programming fills that grid 1 element at a time. At the end, equal GCDs means read the diagonal, skipping the all-empty corner. A hard problem, tamed by remembering just 2 small numbers. See you in the next one.